Good morning. Before showing you the measurements in the laboratory, I would like to present you the method we used. Let's begin from fluxmetric measurements. In defining and measuring the relationship between the field and the magnetization in a magnetic material, we must specify whether we are looking for DC or AC properties. If we are to determine the magnetization curves, we necessarily have to change the strength of the applied field with time. Strictly speaking, we talk of DC curves where this change is accomplished in such a way that every decoded point corresponds to a stable microscopic configuration of the system. In the figure, you can see initial magnetization curves in several types of soft magnets. Curve 1 is a finite type, nanocrystalline alloys. Curve 2, the blue, amorphous alloys, cobalt-based. The 3-1, the magenta, is amorphous iron-based amorphous alloy. And then Gumetal, the number 5 is a grain-oriented iron silicon lamination. And you can see the manganese zinc ferrites is the number 8. The saturation magnetization, saturation induction is very low compared with the iron silicon lamination. And nickel zinc soft ferrites is curve 9. And 10 are iron powder cores, soft magnetic composites. In a fluxmetric measurement, the magnetic behavior of the material is obtained by detecting the flux variation ensuing from the application of a time-varying magnetic field. The fluxmetric characterization most frequently calls for vanishing the magnetizing field. This condition is realized either by shaping the test specimen or by resorting to a flux closing yoke. The latter can be supplied by a magnetizing current, so as to provide both the exciting field and the flux closure. This is the yoke, the flux closure, these are the poles, and you can also supply the magnetizing current EH in order to magnetize the sample. And the secondary windings are here to detect the flux variation. Or different shapes are rings, bulk rings, typical of ferrites, or thin rings, and there are superposed a series of rings, or also typical for nanocrystalline or amorphous alloys. You prepare a toroid by bonding a tape. And this is the hexane frame typically used for iron silicon laminations, whereas the flux closure is produced at the 4 angles. With the ring sample of mean circumference Lm, the effective field is easily obtained by knowledge of the magnetizing current EH. The effective field H is equal to the number of turns N multiplied by EH and divided by the mean circumference Lm. In the figure at the left, you see some pictures of commercial ferrite toroids, different size. And on the right figure, you see the manganese zinc ferrite sample we will measure in the laboratory with the primary green wire and the secondary winding yellow wire. In the middle, there is a sketch of the toroid with the primary and secondary winding proportional to the magnetic induction intensity variation with time. On the left, you see a diagram of wattmeter hysteresis graph setup, which implements digital control by recursive process of the dB/dt waveform, and example of final voltage signal is shown on the right in the primary circuit of the period, that is the blue line. The red line is the secondary circuit over a period. The hysteresis loop shown in the instant is measured at 1 Hz and peak polarization of 1.8 Tesla on a grain-oriented iron silicon lamination using the Epstein test frame. The voltage UH is proportional to the applied magnetic field. The sinusoidal voltage UL is proportional to the peak polarization variation with time. Whatever the specimen configuration, any digital hysteresis graph wattmeter built according to the previous DC test scheme can deliver a most complete information on the magnetic properties of the material over the appropriate range of magnetizing frequencies and define induction waveform, major and minor hysteresis loops, normal magnetization curve, permeability, apparent power, power losses. All desired quantities are obtained in it by numerical elaboration after analogic digital conversion, using high resolution, high sampling rate acquisition devices with synchronous sampling over the different channels. We can achieve excellent reproducibility of results. In the left figure you see hysteresis loop at different frequencies from 50 Hz to 1 kHz in non-oriented iron silicon sample lamination Epstein frame. In the right figure there are hysteresis loop from DC up to 800 kHz for a manganese zinc ferrites to observe the different hysteresis loop, the changing with frequency, the different frequency behavior of the hysteresis loop. Now just 2 words on medium to high frequency measurements. There is an increasing trend towards the use of electrical machines and various types of devices over a wide range of frequencies and with a variety of supply methods, which call for the precise characterization of soft magnetic material beyond the assessed DC and power frequency domain. However, to adapt the conventional measuring setups to the characterization of soft magnets up to the megahertz range might become a relatively complex task. In the figure on the left, you can see hysteresis loop from DC up to 1.8 MHz for a commercial manganese zinc ferrites M30 at the peak polarization of 100 mT. In the figure on the right, you can see the energy loss behavior versus frequency for a fine metal alloy, for a fine metal toroids, crystalline alloy of thickness 20 micron, and this is a transversally annealed sample with the anisotropy induced K of 24 joule per cubic meter. So you have the hysteresis loop and the energy loss behavior. I would like to stress some experimental problems in the medium to high frequency region. First, the flux penetration in the test sample can be incomplete due to the skin effect. Second, the temperature of the sample can appreciably rise during the measurement. A 0.05 mm thick grain-oriented sheet suitably developed for high-frequency applications can display, for example, a power loss of about 500 Watt per kilo at 1 Tesla and 10 kHz. The sample temperature is correspondingly expected to rise at a rate around 1 degree per second. Third, the increase of the required exciting power with the frequency poses a serious limitation on the achievable peak polarization value. If you want to reach 5-10 MHz, we are forced to stay at a low peak induction from 2 up to 20, 50 Tesla, no more. Point 4. Fast analogic digital converters are required to satisfy our requirement of single-shot signal acquisition and real-time analysis. Point 5. With the increase of the magnetizing frequency above the kilohertz range, it becomes important to consider the role of stray inductances and capacitances. This is the most basic issue, the one making the real difference between low frequency and high frequency measurements, at least up to the radio frequency domain, where the wavelength of the electromagnetic field becomes comparable to the dimensions of the test specimen.